In this video, we're going to go over the basics of substitution reactions, and we're going to specifically look at SN2 reactions. So a substitution reaction is one in which one group is substituted by another group, and the one group that gets substituted ends up leaving. That's going to be called a leaving group. So in this case, Y comes in, and it'll come in like this. It'll attack the carbon that's bonded to the leaving group. X is our leaving group, and X will leave. And then that'll leave us with X minus left over. So how does this work, and why does this work? Well, the first thing we need is we need a nucleophile and we need an electrophile, okay? A nucleophile is something that's delta negative or just has a negative charge. So here we have sulfur, and that's a nucleophile. And then an electrophile is something that's delta positive. So this carbon right here is an electrophile. Now, remember from previous notes that halogens are not nucleophiles, okay? Rather, halogens are going to make great leaving groups. And so what happens is the nucleophile attacks the electrophile, but carbon, we know that carbon can only have 4 bonds, and so it must break one of its bonds to accommodate this sulfur group. And the bond that's most likely to be broken is the one with a leaving group. And a leaving group is going to be a group that is relatively stable being on its own, as many halogens are. So chlorine will leave, and we will get this thiol group, this SH group, added or substituted, and chloride will be our leaving group. And how this works is it'll start with a nucleophilic attack and then a leaving group leaving. Okay. So, there's going to be 3 components necessary for substitution reactions. The first thing is we need an sp3 hybridized carbon involved in a carbon-halogen bond. Really, it doesn't have to be a carbon-halogen bond. That's just what we're going to see, but we need a great leaving group. Okay, now, we haven't really focused on hybridization in this class, but what sp3 hybridized means is we need a tetrahedral carbon. And what does that look like? That's a carbon with 1 group, 2 groups, 3 groups, and 4 groups. So for example, if we have carbon with 1 group, 2 groups, and 3 groups, where it's trigonal planar and it has a double bond, this carbon cannot undergo substitution. Okay, it's got to be a carbon with 4 different bonds. Our leaving group, it must be something that can accept electron density. We're going to see in this class iodide, bromide, and chloride a lot, but there's many different types of leaving groups, and we see these large ions that are great leaving groups, mainly because they not only have resonance, but they put negative charges on highly electronegative or large elements. So it's a great thing. We have an inductive effect here. So lots of things that we've talked about in previous units. Okay, and then we must have a nucleophile, okay, because one of our steps is going to be nucleophilic attack. Now, we've gone over carbocations, but here we specifically have carbon halides, which are carbon halogen groups, and I put chlorine here, but it could be bromine or iodide, and we should be familiar with primary, secondary, or tertiary, and so if we remove the chlorine from each of these, what does this carbon group look like? Here, it looks like this, primary. Here, it looks like this, secondary. And I guess I'll draw the R's. And here, it's tertiary. Okay, and so a good review or a good reminder would be that tertiary is most stable, and primary is least stable or very unstable. So, which of the above would likely react in one step? That's going to be our primary or secondary. Oops. And let's see how I want to write this. One step. And I would just go ahead, it doesn't make much sense right now, but this would be a SN2 reaction. And then we have 2 steps. and that's going to be called an SN1 reaction. We'll go over why they're called what they are. Secondary or tertiary can occur in 2 steps. And if it's going to occur in 1 step for secondary, it's going to be a charged nucleophile. And here, if it's going to occur in 2 steps, it's going to be a neutral nucleophile. Okay, and that'll make sense later on. I just want it down on paper. That way, when it comes up, you have it there to reference back. Okay, so one thing that we're going to see is that hydrogen and fluorine will never be great leaving groups. The reason why is that their bond energy to break is just so large that it's not going to happen. Okay, not under normal circumstances. Okay, now let's show how the SN2 reaction mechanism. So in an SN2 reaction mechanism, we have nucleophilic attack. Oops. And then leaving group leaves. Okay, and I would abbreviate nucleophilic attack NA and leaving group leaving LGL. And this all happens in 1 step. So what does the rate of this reaction depend on? It depends on 2 things. Nucleophilic attack, nucleophile attacking, and leaving group, leaving, and these are going to happen simultaneously. Okay, and so that's why it's called an SN2 reaction, is it depends on 2 things. And so if you've taken other chemistry classes, you may not have seen this, but we are dependent upon the concentration of our nucleophile and our leaving group. Okay, so our rate law is overall 2nd order. Now, if we have a leaving group and it has stereochemistry, meaning that it's on a chiral carbon, then we're going to see an inversion of stereochemistry. Okay, so if bromine is my leaving group, and I don't like how this has been drawn, I'm going to draw it a little bit better. Let's say I have a wedged bromine. Okay, it looks like this. And I have an SH group, and typically it's very common for the reactant that we're less concerned about, that, but still needs to be there, of course, for the reaction to occur. It's very common for us to write it above the arrow. What's going to happen is bromine is pointing out of the page, and it's very hard for me to show this on video, but imagine the front side of your page, bromine is occupying. And so if this nucleophile is going to attack, the sulfur can't come in from the front side. It has to come in from the back side, and this is going to be called backside attack. And so because it comes in from the reverse direction, bromine leaves, gets kicked out. We're going to have the SH group have stereochemistry that shows that it came from the opposite direction. And then bromine takes its electrons and leaves, and so we get something that looks like this. Okay, so with SN2, we get an inversion of stereochemistry only at the side of the attack. So let's say we had some methyl wedge down here. That methyl wedge would still be there because that's not part of the reaction. Okay, sterics refers to how crowded an area of the molecule is that you are reacting or studying, and then steric hindrance is specifically referring to how an area is crowded, and this prevents reactivity at that site. And so what we need to know is less sterically hindered electrophiles react more readily under SN2 reactions. So for example, we have this bromine group. Something's going to come in and attack that carbon. Bromine's going to leave. That's going to happen to all of these. And as we get more groups, it makes it harder for our nucleophile to get in there and attack. And so we see that tertiary carbons never ever react via SN2. Okay, you will get that down just fine. That's what we were talking about here with SN2. Notice we've got primary and we've got secondary. Primary is going to be fast. This is going to be slower. Okay, for SN2. And we'll talk about SN1 in the next video. Okay, and one of the things, if you've seen activation energy charts before, is when you get to tertiary, the energy required to have a tertiary carbon undergo SN2 reactions is just so high that it's not likely to happen. Now, it has happened before, but it's not going to happen under normal circumstances. Okay, so let's talk about this carbon on each of these. That's where our leaving group is. Which one would you rank to occur the fastest, meaning that it's the least crowded? I would say that one. Now, which one would you say is the slowest because it's the most crowded? I would say that one. And then between our right bromine carbon group and our left bromine carbon group, I would say number 3 is just a little bit slower than number 2 because those methyl groups are one more carbon away from that bromine. It makes it easier for our nucleophile to attack with those methyls further away. Okay, now here we want to think about this carbon. It's not a bad idea. Up here, they were all secondary, so I didn't bother labeling them as primary, secondary, or tertiary. And here, we've got secondary, or actually, I'm wrong there. This is primary, secondary, and then tertiary. It's the number of R groups attached to that carbon, and bromine does not count as an R group. And so I would say this one occurs the fastest. This one occurs the second fastest. That extra methyl slows it down just barely, not really a huge amount. And then since this one's secondary, that'll be 3. And then this one, tertiary, does not react via SN2. Okay, so now what I'm going to do is these are the first 2 problems on the homework. I'm going to show you how this works. And every single one with SN2 is going to be very similar. So you want to just recognize the pattern and then follow the pattern. So we want to draw a detailed mechanism for the following reactions and use correct arrows to show the nucleophilic attack and leaving group leaving. So the first thing I'm going to do is I'm going to recognize that this is primary, no problem. And whatever carbon is attached to bromine, that's going to be my electrophile, okay? Now, I've got sodium. We know sodium is always positive. It's just a spectator ion. And whatever sodium is sitting next to will be negative. So here it's oxygen. And so that is definitely a strong nucleophile. What's going to happen is my nucleophile is going to attack my electrophilic carbon. Okay, so I think it's helpful to label your arrows. Simultaneously, though, because this is SN2, 2 things are happening at once, this leaving group is going to leave, and we'll abbreviate that LGL. So what do we get? We're going to get an OH group substituted for the bromine, and then sodium is still there, and then bromine has left and taken with it its electrons, and so bromine will be negatively charged. Okay. So that's a basic SN2 reaction. Let's look at another one. Here, these are going to get very similar. I see that I've got a secondary carbon, and I've got a charged oxygen, so that's going to be a strong nucleophile. My nucleophile attacks that carbon. Simultaneously, the leaving group leaves. This carbon is a wedge. We didn't touch it. No arrows touched that, so we'll put a wedge there. You don't have to color in your wedges. You're more than welcome to, but oftentimes I won't. And then since this bromine was a dash, that means this oxygen is going to be a wedge because we get an inversion of stereochemistry. So inversion Okay, now here's what's weird is a lot of people will just put an oxygen, but notice oxygen is bonded to a methyl group, a CH3 group, and that group is going to come with it. What's left over is sodium, positive, and then bromide, negative. Remember, sodium is just going to follow wherever the negative is. We did not touch this methyl over here on the ring, and so it stays put.